The first question I have here, maybe, each of you can present your views. And the question goes like this. If one were to move the storage systems to the backend network on the GPU fabric, what kind of networking challenges do you foresee?
Can I?
Yes, please.
Yeah. So far storage network has been usually connected through the front-end network, but this is coming into the backend network because of distributed inference, which requires KB cache, backfill, and those things on the critical path between GPUs. So what I can immediately think of is, ensuring that sort of GPU direct storage kind of thing, moving data in and out of GPU and into the storage with as little overhead as possible, bypassing CPU. Those kind of things will come as a challenge, and integrating these things with the framework, and then also coordinating sort of network sharing between the training traffic and distributed inference traffic. Those things will probably come as new challenges.
Okay.
So maybe I can add that another challenge I can think of is maybe the heterogeneity in terms of the network cards that we use for storage systems versus GPU backend network. And this might mean that we have to upgrade our storage infrastructure or coordinate to catch up with the bandwidth for the GPU network.
So interop across heterogeneous NICs would be critical and has to be addressed. Cool. Yingjie, would you like to add anything?
If we move this storage to GPU to GPU server, I think we are expecting a mix of traffic on the network. It includes the storage traffic. It also includes the training traffic, and they have different preferences. Some of the, for example, the training job, they are more sensitive to latency, but they are small. Right, and the other data, like a checkpoint data, host bearing data, they're bulky, but they are able to bear some latency. So, on network perspective, we need to identify those different characteristics of this traffic, and we may need to apply some mechanism to guarantee latency sensitive traffic won't get latent.
Okay, that's very good. So essentially, how do you make sure latency sensitive and latency tolerant traffic can coexist on the fabric? And can you bring in some QoS mechanisms to guarantee the service that is expected? Takshak, anything you would like to add?
Yeah, definitely the application needs to be aware about the available backend NICs, because there could be like 8 backend NICs for the GPUs. They also need to make sure that outside of the CPU-based normal socket communication, they have to hop onto the RDMA-based stuff. So there will be a lot of churn into migrating into it.
Cool, thank you. Let's go on to the next question. Maybe, Chang, you can help us answer this question. Why is network virtualization so important for cloud-based GPU networks? What if you don't do virtualization?
Yeah, so the main issues are probably on 3 dimensions. One, scale. So the number of endpoints that we have to deal with can easily exceed the switch-based isolation technology's scale. And one customer is not just one isolation group, right? They need multiple isolation groups, especially think about some inference as a service customers. They also deal with hundreds of thousands of their customers, and then they want isolation on our cloud. So that's one aspect. The second aspect, security. Increasingly, more and more, this data is very privacy sensitive, and data center is shared. So they really want to make sure that every single byte is actually cryptographically secured. And then the other feature sets, such as velocity, and then ease of upgrade and high availability. We believe that software-based and those solutions are a little easier to deal with.
Okay, the first insight is very useful. Even for like multiple workloads from the same tenant, you need to provide isolation, and hence virtualization is the way to go. Okay, thank you for that. Takshak, looks like this question is for you. How does multi-NIC solution compare with NIC bonding approaches?
Oh yeah, I think we can consider as a generic solution and very niche solution. So if we consider a normal generic solution, yes, NIC bonding can be applied. You can add all the physical NICs into one single NIC bond and then do the distribution. But the challenges here is that the NIC bonding will add an additional hop for every packet. So when the packet is outgoing, there will be a buffer at the NIC bonding level, which has to be processed by the additional soft IRQs, which will add the CPU cycles and which will add the overhead ultimately. So these generic solutions doesn't work for the scale what we are talking here.
Okay.
And that's where we wanted to avoid that using the BPF-based solution.
Okay, cool. Weilong, in your talk, you touched on ASAPD daemon. What are the challenges that you came across in ensuring, seamless, hitless upgrades of this daemons like this?
Yeah, so there are two major challenges I can think of. One is these software, they're very tightly coupled with, let's say, the firmware of the NIC. And in the massive fleet that we have, you usually end up with multiple versions of firmware running at different machines, even for the same cluster, same customer. And in our software, we have to build into the capability to deal with that. So basically, multiple versions. You can think of multiple versions being packed together, and at runtime, you decide which one to kick off based on the firmware. Yeah, that's like one big challenge. The other challenge is, ASAP is just one system software in the bundle.
Okay.
You have like, let's say, many other softwares, and sometimes they have dependency. They have order requirements in terms of startup. And when you do rolling upgrades, you have to be very careful to ensure, the proper order of operation.
Okay.
Yeah.
Okay, cool. Yingjie, you touched on, eCMP-based solutions, right? How does distribution of traffic volume across flows would work here? And how do you handle elephant flows?
Yeah, so from the front end network point of view, so we see checkpoint data, we see data ingestion, we see house bearing. Some of them are very big flows like checkpoint and house bearing, and some of them are small like data ingestion. And in the front end network, we see a mix of them. So there could be elephant traffic, but ECMP is succeed when there are many small flows. It doesn't handle elephant flows very well, especially if there is only a few of them, because the hashing cannot guarantee that these few flows can be evenly distributed among NICs. They might be just gathered on a few of the NICs.
Okay.
Yeah, so we could do some like routing or forwarding level of solution of splitting the NIC, splitting the flow into multiple small flows on the network side, just like what we already done in the backend network. But we also can rely on the application level. If application level is aware of their flow being so big, they can also split the flow into sub-flows, many sub-flows. This can also improve the efficiency of the ECMP.
Okay, thank you. Maybe Takshak, you can take this question. How does your solution handle failure scenarios, especially NIC failures or link failures on the fabric while checkpointing is in progress?
Right. So kernel does handle if the link is down, kernel just detect it. But if the link is up and is still doing the backhaul, that won't be detected. So using the kernel existing mechanism, the link over does get handled.
Okay. And anything specific to the fabric link failures that you have to be concerned about?
Yeah, if the link is down literally, then kernel will detect it. But if it is not, then it will be just the backhaul traffic.
Okay, sure. Chang, maybe you can help us with this question. How can these unique demands that ML workloads exhibit on the network, especially in context of cloud networks, help us, drive innovation in virtualization space? Anything unique to these workloads that we should be aware when we think about virtualization solutions for GPU clouds?
Good point. So although we showed a very good high performance and very tight latency, if you go deeper, you can argue that, hey, all those things work well because your workload happens to fit on that NIC data plane cache. For example, the total number of PSP connections that we have. If that explodes to millions, of course, we won't be able to achieve that kind of great latency. Luckily, right now, we didn't have to do any particular optimization of the stack, either nickel or nixel or even at the workload level. Because we're cloud, we cannot enforce that. There's only so much we can do that. But yet, luckily, these workloads happen to fit in that scale well enough. Will it continue to do so with increasing, NIC speed and so on? That's a good question. I hope so. And some other companies like Meta can optimize the full stack to your workload, so you have more leeway. Unfortunately, cloud doesn't. So that's one of the big challenges that we'll have to live with. The evidence that we have collected by looking at nickel layer and so on indicates that there's a significant room here, right? I mean, the actual working set size is much smaller than modern NIC data cache size, but still, it's something that we have to nervously, look into going forward.
Okay. If I were to summarize, when you have the opportunity to have insights of your workloads, you can really create a tightly optimized system. But when you are like a public cloud provider, you cannot come up with a one-size-fits-all solution, though there are only a limited set of solutions you might roll out into production. Okay, cool. Yingjie, in your talk, you mentioned ingress solution, and you talked about the IPs being announced to the rack switches. Any reason we need to do that instead of announcing NIC subnets with ECMP to the rack switches?
Yeah. This is due to the multi-tenancy. So on a single host, we might support multiple customers' jobs. And each of the job has the task IP assigned from the same NIC, same subnet. If we announce the subnet, we are not able to differ these training jobs. And also, for example, if we want to do some resource isolation, we may just want this job to use NIC 0 and 1, that job to use NIC 2 and 3. Mm-hmm. So in this case, announcing this individual task IP can give us better granularity on controlling the hardware resources.
Okay, thank you. That brings us to the end of all the questions we had. Thank you everyone for submitting your questions, and let's thank the speakers one more time. Thank you.